To those of you in the Zoom, sorry while I get everything set up. Can you all let me know if you can hear me okay? Okay, great. I'm gonna leave this chat window where I can see it while I get started on everything. So there are 3 requests in the problem solving session. Oh, I'm going to apologize in advance. I got sick this weekend and my mouth and throat are still kind of weird, so sorry if it's hard to understand me sometimes. But there were 3 requests. Problems 2, 4, and 5 in section 12.7. So I'm just going to go through them in order because that's the same order you all will work on them in. So, problem 2 in section 12.7 is writing the 3 different types of coordinates for a cylinder. And I'm going to do it for the numbers in my web work right here. So I'm going to sketch it out real quick, even though there's a picture, just because it helps to see non-coordinate system. So they tell us it's a cylinder with radius 3, and the bottom is at -4, and the top is at 4. So it's kind of like this, where the radius there is 3, or the width along the x and y axes is going to be 3. And so a slice of that cylinder is going to be an actually centered circle, not like what I just drew, but with radius 3. So it's going to intersect all the axes at 3, and it's the same going up and down all possible heights z. And so we're asked to set this up in Cartesian, cylindrical, and spherical coordinates, spherical being the hardest one. But I'm going to go through and do all of it because you all didn't specify. To only do one part, I mean. So for Cartesian coordinates, we're just looking to set something up. Do they say we need a special function? No, we're finding the volume. So this p of xyz is just whatever you have to put inside to integrate it. It's going to be where our kind of change of variables for dv goes. But there is none. Oops, they want to do it in that order. Fine. So Cartesian is in order dy, dx, dz. And then we can just start filling in coordinates kind of as they're easiest for us. So they told us that z is between -4 and 4. So I can go ahead and do that right away. And then to do my dy dx, because I'm only thinking about y and x, I can focus on this second picture that I drew right here, where it's a circle with radius 3. So that's I'm just going to call this region R, and that's going to be x squared plus y squared equals 9 is kind of the boundary for it. If you all have not committed the equation for a circle to memory, you should for this section. And so if I wanted to solve for y, because it's inside, so I need is bounds to depend on x, I would have y squared is root 9 minus x squared, or y is plus or minus root 9 minus x squared. Oops. So to start, I shouldn't have had that root there. Whenever you have y squared equals something, we have to remember that we get these positive and negative branches. That's really the one place where something goes wrong here. So we're negative root 9 minus x squared to positive root 9 minus x squared. And then just to kind of show you that positive root 9 minus x squared is this part right here. And that negative root 9 minus x squared is this part right here. So kind of those bounds are saying we start down here and go up here for any value x. And then our x bounds just have to be sort of if you smushed this shape down and checked what interval it shadows on the x-axis. That's what we have to fill in. And so for us, that's going to be taking x from negative 3 to 3. Because the furthest left that x is over here at minus 3, and the furthest right that x ever is over here at positive 3. And then at that point, we've filled in the coordinates for Cartesian. That p would just be like 1, because we need nothing special to create dv in Cartesian coordinates. We only need that for spherical and cylindrical. So then moving on to cylindrical. The order we do it is dr, d theta, dz. Okay. So between Cartesian and cylindrical coordinates, z never changes. So you can go ahead and keep that same z bounds that we had before. So the variable z stayed the same. And our bounds for z didn't depend on x and y, so there's no need to change them when we switch to r and theta because they were always constant numbers. So then we just have to figure out r and theta. And again, because we already took care of everything z related with minus 4 to 4, r and theta we just consider in the region capital R over here that I drew separately. And so in this case, it's a little bit easier to see what the bounds are. We don't have to solve for anything. We know that radius, little r, is from the origin. How far out do you go, and how far into the origin do you go? Actually, I'll center that a little bit more. So the smallest little r ever is a 0 because we fill in all the way to the origin. So if the middle of your xy plane is filled in, that means r equals 0 is the lower bound. And then the furthest out r can go is the radius of the circle 3. So furthest in is 0, furthest out is 3, and then you don't go past that. Oops, okay, I'll just leave that arrow there. And then theta is how far around the x-axis we rotate while still being in our shape. So since we start here along the x-axis, theta equals 0 is where we start. And then we spin all the way around until we reach that x-axis again, which means we've gone a full 2 pi. So then theta was the middle one, so it goes there. And r was the first one, so it goes there. And then we actually do need something special here. So whenever we switch dv to polar or cylindrical coordinates, we need to remember to add in this r. So that would be the replacement for this p function right here. And then spherical, what I'm going to do is I'm just going to erase everything else I have so far so that there's plenty of room for this one because there's a lot of parts to it. Erasing takes forever. I'll just cut it. There. Okay. So spherical is the hardest one. They tell you spherical is twice the top half. So they're actually setting up the integral for only the top half, and then you would double it times 2 to get the full shape. And then within that half, you actually have to do 2 separate integrals. So I hope there's enough room here. So let's go ahead and get started on that next. So the place where these two things are being set up is for phi from 0 to arctan 3/4, and then from arctan 3/4 to pi over 2. And phi, if you all remember, I guess we'll use that color. Phi starts along the z-axis and then rotates down towards the xy plane. So right here is actually going to be the angle phi that we end up splitting things by. Arctan 3/4. And what's happening here is that there's something about the geometry of this problem where it changes if you start thinking about angles here compared to angles here. So up to the solid line that I've drawn, every time you kind of come out from the origin and onto the surface, you're poking points along the flat circle top of this cylinder. So the distance from the origin to the surface is the distance from the origin to that flat disk. And distance from origin is important because that's rho. Once you cross that solid line I drew, the distance from the origin to your surface is the distance from the origin to this like can shape of the cylinder, defined by x squared plus y squared equals 9. So the reason for this divide is because the bounds of rho are going to change depending on what angle you've reached in your object. So then the thing that they've already told us up to this point is that we're thinking about two different phis. We're thinking about first the phi that goes from 0 to arctan 3/4, and then the phi that goes from arctan 3/4 out to pi over 2. And that pi over 2 is going to be going from the positive z-axis to the xy plane. So we're doing really just this top half of our cylinder. So without having to solve for anything, we already know that we have to fill in the phis that way because that's what they told us to do. And then I'll go ahead and say that it's also pretty easy for us to pick theta because we already did theta when we did the cylindrical coordinates, and theta is defined the same way in spherical and cylindrical and polar coordinates. It's this angle that I drew an arrow about already. I'll erase it and do it again. That way. So we know that theta goes from 0 to 2 pi. And so really the only tricky part is that rho we haven't defined before and we haven't been given, so we have to figure that out. So I'm going to call these parts 1 and part 2. So in part 1, rho has to be the distance from the origin to this disc shape. And then for part 2, rho has to be the distance from the origin to this actually cylinder shape. And so it's important to write down the functions for what we know about these two regions to start. That way we kind of can figure out how to solve for. I'm sorry, my dog has a stick in a bag. You can't chew that right now. Okay. So we can just write down in Cartesian coordinates what we know about either of these regions, this one or that one. So for part 1, what we really know is that z is at 4. And then for part 2, we know that x squared plus y squared is equal to 9. And then important to note that even though I drew just like these bounds of the shapes and shaded them in, we're finding the volume that fills up all the space between. So in either case, this was still a solid object that filled in all the space to the origin. So we know that rho is going to start at 0 in either case. And then real quick on the side, I have to pull up the definition for spherical coordinates because I don't commit those to memory. But hopefully you have them somewhere in your notes and maybe you'll find them faster than me. So in spherical coordinates, z is equal to rho cosine phi. And if we also know that z is equal to 4, that means that 4 is equal to rho cosine phi, or rho is equal to 4 over cosine phi. I didn't give myself enough room. So then my bounds for phi are going to be that it has to go from 0, we fill in all the space to the middle of the surface, and then it goes up to that flat disk defined by rho equal 4 over cosine phi. So I just do 0 to 4 over cosine phi. For the second part, I'm just going to go ahead and erase this right away because I know there's not enough space. We know that x is equal to rho sine phi cosine theta, and that y is equal to rho sine phi sine theta. So we could plug in those substitutions, and now we know what the surface is called in spherical coordinates. So rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta is equal to 9. And from here I just have to use some fancy trig. I can pull out a rho squared sine squared phi times cosine squared theta plus sine squared theta is equal to 9. But cosine squared plus sine squared is 1. So rho squared sine squared phi is equal to 9. Or, coming all the way up over here, we've got rho squared is equal to 9 over sine squared phi, or rho is equal to the square root of 9 over sine squared phi. Rho has to be a positive number. It starts from 0 and goes up, so that's actually going to be 3 over sine phi. And that would be how you write the bounds for that last part. And since there are 3 problems, I've got 20 minutes for each, but real quick I want to pause. Are there any questions about this one? I'll leave that up while I tab over to the next thing, in case anybody types a question. You all could just type no question if it's okay to move on. Okay, cool. I've got no question, no question. Cool. I'm going to assume that David speaks for everyone here, that there are no questions. So next request was for problem 4. We're told that we have a cone given by this equation topped by a sphere of radius 2. Again, I'm going to draw it. So since the sphere has radius 2, we know that it goes up to height 2 over there where we're looking at it. And then this bottom part is the cone, which they tell us is z equals root x squared plus y squared. Something they don't tell you that you need to know is that sphere with radius 2 means x squared plus y squared plus z squared equals 4. So just like equation of a circle, if you don't know that thing, it would be good to remember it now. So we again have to write this in Cartesian, cylindrical, and spherical coordinates. So for Cartesian, again, we don't have to worry about anything special for that function. Oh, shoot. When I did this one, I forgot to write, in the middle here, we have to put that rho squared sine phi, cosine. Let's see, at a glance, is it anywhere? Okay, I do not remember it right now, but whatever that thing is that I told you all in your notes that always goes with dv, I think it has a rho and a sine phi in it. Make sure that you put it there for your p function. And then at the end of this video, I will Google that and write it down. Okay, but so there's nothing special we need for Cartesian coordinates. Oh gosh. Sorry, a YouTube video for it open. Okay, so first we're going to do our z-bounds, and if you filled in the part where the equation for a sphere is given by this, then you already have everything you need for the z-bounds. So the sphere rearranged to z equals something would be square root z4 minus x squared minus y squared. There's a plus and a minus. The plus part is above the xy plane and the minus part is below it. So we actually only care about the positive part here. And the cone was given z is root x squared plus y squared. Z bounds are lowest possible point on the surface to highest possible point on the surface. So the bottom bound is going to be that cone, x squared plus y squared, the square root of that. And the upper bound is going to be the sphere, the square root of 4 minus x squared minus y squared. To get dy dx, we have to think about the shadow that this shape casts in the xy plane. So kind of imagine shining a light down on this ice cream cone type shape. You would get a circle cast below it. And so that's what I drew here, is a circle in the xy plane. But we need to know how far out that circle goes. So I know it's a circle, but I don't know how wide a circle it is. Taken another way, anytime we don't know what to do next with setting up integrals, we set the two bounds equal to each other. So I know that the widest part of my cone is right there. So that's going to be the shadow that I get in the xy plane. And that happens to be where the sphere and the cone meet each other. So if I set the equation for the sphere equal to the equation for the cone, I will get this region. So 4 minus x squared minus y squared is equal to x squared plus y squared. 4 minus x squared minus y squared is actually equal to that without the square roots. I just square both sides. Or 4 is equal to 2x squared plus 2y squared by adding the x squared and y squared from the left to the right. Or 2 is equal to x squared plus y squared. So it happens that this actually goes out to distance square root 2. I wrote it this square root 2 way because that's the radius, that's the way you're used to usually seeing the formula. So my region R, first I want bounds for y in terms of x. So if 2 is equal to x squared plus y squared, that means y is equal to the square root of 2 minus x squared. And remember that there are positive and negative branches of that. So negative root 2 minus x squared is less than or equal to y is less than or equal to root 2 minus x squared. Okay. So I can go ahead and put those on my bounds right now. And then to get my x bounds, I could go ahead and right now I know this is a circle with radius square root 2. So I know my x goes from minus root 2 to positive root 2. But supposing you didn't see that, you could also say I have two bounds, I'm going to set them equal and see what happens. So you would get minus root 2 minus x squared is equal to positive root 2 minus x squared. A negative is only equal to a positive if both those things are equal to 0. So then just doing the algebra, you would get to x goes from negative root 2 to positive root 2. And then that's how you do that part. And there's still no questions in the chat, so I'll go ahead and continue to the cylindrical one. Since we're going to reuse a lot of this, I'm just going to delete the parts I don't need anymore. So now we're thinking about doing it in order dz, dr, d theta. Unfortunately, all of that needs to go. Cool. And just like I said for the last problem, z is the same in Cartesian and cylindrical coordinates. So technically, its bounds are still this. The only difference is now you can't use the variable x or y. You have to use the variables r and theta. So you have to convert x and y to be r and theta. And you can do that really easily for this problem by remembering that x squared plus y squared equals r squared. So root 4 minus x squared minus r squared is, root 4 minus x squared minus y squared is the same as root 4 minus r squared. And root x squared plus y squared is the same as root r squared. or r. So our bounds for z are still going to be the cone on the bottom, the sphere on the top, but now we write them in polar type coordinates. So it's r below and root 4 minus r squared above. And then dr d theta is still going to be given as the shadow that our 3D shape casts in the xy plane. So it's going to be this whole region right here, which is a circle. Even if I at first wasn't sure what the radius was, I always knew it was a full circle. So my theta would go from 0 to 2 pi, just like it did for the other circle shape we did in the previous problem. And it's a filled in circle, so we know that the radius starts at 0. And so the only tricky part here is figuring out how far out that r goes. And so I already went through trying to find that radius once before. I know it goes out to root 2. I could go ahead and, write that down. But the way you would do that if you didn't see that connection is you would again say, okay, I've got an upper bound and it has to be equal to a lower bound. And then I'm just going to try to solve for r. R is always positive, so I get the positive square root of 2 as its upper bound. And then that would get you the cylindrical coordinates. They tend to be pretty quick after the Cartesian, because they have one thing in common. Any questions up to there? I'm gonna figure. Okay, thank you, David, for typing things. So then last on our list is spherical coordinates, and those are given to us in order. Oh, sorry. I should have been clear to state, whatever, I won't put it back. But you did have to specify that P, it's the same one as you got on the previous problem, it's R. For converting dx dy dz to r dr d theta dz. So then the last thing we have to do is spherical coordinates. And these ones are really not going to use anything else, so I'll go ahead and erase it. Oh. Okay. So then let's try to figure out what we know. Rho is a radius of a sphere. It's the distance from origin to surface. But kind of if you always think about being the same distance from the origin, you are a sphere. Just like in polar coordinates, the same distance from the origin r is a circle. So kind of one hint is every time you're given a problem and you're said that the bounds are a sphere, you should immediately take that radius and make it rho. The same way when somebody gives you a radius for a circle, you probably don't stop and think about it. You just say, oh, that's going to be my r. So you could right away say, my bounds for rho must be from 0 to 2 because I'm told I have a sphere with radius 2. And I'm also told that this is like a solid object, so it goes all the way to the origin when I'm filling it in. The other way you could try to figure it out is by starting from the origin. You can draw rho as like an arrow, but even if you try to get as close as possible to this cone, the final distance from the origin to the surface is still going to be on the sphere every time. Because A cone has all its edges at the origin. So if you start at the origin and point to the surface, which is what rho does, you're never going to actually land on the cone. You're just going to run along the cone. The other one that's going to be pretty straightforward for us, actually, let me just undo those, is going to be theta. Theta is rotation around the xy plane. And we had previously drawn the projection of this surface into the xy plane and saw that it was a circle and said that our bounds were 0 to 2 pi. So at some point we knew theta in a different coordinate system, but that theta is the same one. But if you're trying to visualize it, sort of theta is like if you took a slice of your surface, oops, like this, and then you went ahead and rotated it around the xy plane to actually fill in the rest of your surface. What amount of rotation would you need? But to make the full shape out of that weird little shark fin that I just drew, you would need to go from 0 to 2 pi. You would have to spin all the way around the z-axis. If you're looking down the z-axis, there are no gaps in the surface, so theta has to go from 0 to 2 pi. And then phi is the last thing that we have to fill in. And phi is the angle that goes from the positive z-axis down to the surface. So since we're filled in all the way to the positive z-axis, if you're looking down from here, you would see like no hole in the middle. That tells you that phi has to start from 0. And then all we care about is how far down you would have to go, rotating from the positive z-axis towards the xy plane to fill in all this space. And so we just need to know what this angle is right here. Oh, I guess I'll write in words. And then if you kind of look at the cone, you might say to yourself, okay, this is like a 45-degree angle, or like pi over 4. So that's one way to arrive at what phi is. Sort of like, you know that for a shape of a cone, z squared equals x squared plus y squared is like a proportional change in z to change in x and y. So you would expect that to be exactly down the middle of the divide between z and the xy plane, exactly pi over 4. But if that didn't occur to you, the way you would have to do this would be, okay, I know that phi ends at that cone, z equal root x squared plus y squared, and then try to solve using substitution of variables what phi would have to be. So let's see what's the easiest way to do that. The easiest way to do that is to look at kind of a slice in like y and z. Where x is 0. So I kind of took that same slice that I drew before, that shark fin thing, just kind of smush this whole thing to x equals 0 and look at it in 2 dimensions, y and z. Then z equal root x squared plus y squared is z equal root 0 plus y squared, or z equals y. So at that point you might see easier the one-to-one relationship, you know this has to be 45 degrees. But if even that didn't connect yet, you would just have to go and do plugging in the variables, which now I have to Google again because I didn't save the page I was at. So if you know z equals y at this bound phi that you're thinking about, and you know z is rho cosine phi, and you know that y is rho sine phi sine theta. When x is 0, this is looking at well, it has to be true for any theta at all. So you can kind of say that I guess cosine phi has to always be equal to sine phi, which is again only going to happen at that perfect 45 degrees. Right now, off the top of my head, I can't figure out what value theta you actually have to plug in here to get that. My thinking is that it's theta is pi over 4, but it's really hard for me to visualize, and I don't want to slow down too much here. So I'm sorry if that's not very satisfying. You all can ask me about it when I've thought about it more in class tomorrow. If this, like, you see it doesn't connect, if you want to know how to calculate it, I am happy to do that in person later. Any questions except for what is that theta? Okay, thank you, Macy. Sorry. So even though I spent so much time trying to describe what to do if you don't have intuition for phi, spherical really was the easiest coordinates for this one. They're all constant. And then here you just have to plug in your weird rho sine phi, whatever's supposed to go there that I can't remember. So real quick, I guess it'd be worth, it'd be worth talking about. Were we looking at that? Did I do the wrong problem? No, okay, I just went back too far. Okay. So real quick, something you should be critical about is for all these different coordinate systems, what's the easiest one to do? For this one, I would argue that cylindrical coordinates were the easiest because you didn't have to mess with the square roots on the y and x axes, and spherical were the worst. And it makes sense because this is a cylinder. And for this shape, spherical was the easiest. Maybe cylindrical second, Cartesian last. And that wouldn't be necessarily obvious except for that this is actually just a segment of a sphere. So that's why it's so easy in spherical coordinates. The last request was for problem 5 in section 12.7. Use cylindrical coordinates to evaluate this integral. So I'm going to go ahead and write that down. Root x squared plus y squared dv. Around the region E is between 9 minus 9 times, z equal 9 minus 9 times x squared plus y squared, and the xy plane. So for setting this up in cylindrical coordinates, let's give ourselves lots of space. We know that dv is equal to r dr d theta dz. And I actually already know from looking at this that I'm going to have to put dz on the inside. So I'm going to write that dz dr d theta. If you didn't spot that right away, you would just have to change it a little bit later. And then we know that x's and y's are going to have to go away. So root x squared plus y squared is root r squared or r. Using that same idea we used when we did cylindrical for this shape, I think. Oh no, it was this shape. That x squared plus y squared equals r squared. So then I replaced that root x squared plus y squared with this r. And the other r came from dv. And then from here I just have to set up the bounds in cylindrical coordinates. And so I was able to do this without even fooling with the description of my region. And I think it's the thing that you all will be able to do even if you can't visualize your shape on an exam. So even if you get tripped up by whatever region you're being asked to integrate over, at least set up what you know you can do, and then proceed with everything else. So I'm going to go ahead and sketch this shape for us. So they tell us this is a circular paraboloid, which isn't super helpful to me personally. Instead, I can think about, I'm trying to draw this shape, z equals 9 minus 9 times x squared minus y squared. So when x and y are 0 at the origin, I'm going to get z is 9 minus 9 times 0. So I know that my shape has to start up here at 9, if nothing else. And then there's exactly one point where x and y are 0 and z is 9. Kind of going the opposite way, if I wanted to be down here in the xy plane, that would be when z is 0. And it's equal to 9 minus 9 times x squared minus y squared, or 9 x squared plus y squared is equal to 9, or just x squared plus y squared is equal to 1. So if I'm down here where z equals 0, the shape of my surface is a circle with radius 1. So that's me drawing a flat circle in the xy plane. And then my surface is just gonna like connect those two regions that I just identified. So it's kind of like an upside down bowl shape. So maybe you looked at this and already assumed it was a bowl shape, and that's good. If you could have looked at this equation and said that's something that points down and is kind of shifted up on the z-axis. But if you don't know, try plugging in 0 for different variables and see if you can kind of like puzzle out the shape. And I'm going to go ahead and keep right here. It's important to me, I think, that the place where it hits the xy axis is this circle with radius 1. Oh, that's not erasing. Okay. The other thing I'm told is that I end at the xy plane. So that's this part down here where I actually just drew that shape. And it happens to be when z equals 0. So if it's not like second nature for you to see xy plane, think z equals 0, or see xz plane, think y equals 0, that's a good thing to kind of like practice in your head. That's important Because supposing you couldn't do this to draw the shape and you only had the information given in the problem, you would use z equals 0 to kind of turn everything into just simple algebra. So I know that I'm between z equals 0 and z equals 9 minus 9 times x squared plus y squared. So those are my bounds for z. The only tricky part being that x squared plus y squared is r squared. So since we're doing cylindrical coordinates, we need to make that substitution. And then once you have two bounds on one of these problems, you can usually fill in the rest, even if you can't visualize it by setting things equal. So once I have my z bounds, my r and theta bounds are going to be the shadow of my object in the xy plane, it's that shaded in circle I drew before. That's a circle with radius 1. And so I could right away say, okay, my radius is 1, r goes from 0 to 1, and it's an entire circle. Theta goes from 0 to 2 pi. If you hadn't figured out this visualization, the thing you would do is say, I don't know what to do next. I'm going to set my bounds equal and see what happens. So you would get 0 equals 9 minus 9r squared. 9r squared is equal 9. R squared is equal 1. R is positive 1 because we always choose r bigger than 0. And you would get to the same place. The only thing is that without visualizing it, you might not know which goes on the bottom and which goes on the top in that integral. You might accidentally swap those, but you would still get to r should be 1 in the end. And then theta, if you hadn't figured the rest out, would be a wild guess at this point for you. Having no other information, say it goes from 0 to 2 pi, that's your best bet. Or you might key into the fact that they say it's circular and they never tell you a way to break up that circle, so it must be the entire circle. Or if you manage to draw it, you would know that we are doing 0 to 2 pi because there's no gap rotating around the x-axis. So that's setting it up. And then evaluating it isn't too bad. I say, and then surely it'll become a whole mess when I try to do it. But we've got 7 minutes. Are there questions? Cool. Then I'm going to try and do it. I just simplified that r to an r squared. So my first bounds are z. So I'm actually even going to pull out this r squared as a constant as far as z is concerned. And I'm looking at 0 to 9 minus r squared dz on the inside, and then I'll think about dr and d theta after that. So that becomes just z evaluated from 0 to 9 minus r squared. Which is just 9 minus r squared minus 0. And then once I simplify everything, I've got on the inside integrating with respect to r. I think 9r squared minus r to the 4th. Honestly, the thing that goes wrong for you all in this is just forgetting like which variable is staying constant and which variable you actually have to integrate. So we're integrating r here. So it's going to become 9r cubed turns to 3r squared, and r to the fourth turns to 1/5 r to the fifth. And I could check that for myself and make sure when I take a derivative, I get what I started with, because I'm not very good at remembering those things. And then we evaluate from 0 to 1, which is just going to give us 3 minus a fifth minus 0, which I don't especially want to do, so I'm going to leave it like that. And if you were taking an exam, I would say do the same, because adding fractions is not super important. Oh no, my screen timed out, sorry. Adding fractions is important, just not on a Calculus 3 exam. So that's a constant, whatever it is. And then when you integrate d theta, even though theta is a funky variable, that's just integrating a constant, which gets you theta back out of it. Evaluated from 0 to 2 pi, which is just 2 pi minus 0. So I think that's the answer. I'm not 100% sure. I could have made a mistake in there, but I'm going to stand by that one. And then I'm going to pull up the chat to see if there are any questions that people have. And at the same time, I'm going to Google what is dv for spherical coordinates so I can write that down. Oh, great, it was rho squared sine phi. That's exciting. I thought I wrote down rho squared sine phi somewhere. Oh, I did rho sine phi. Okay, it was supposed to be rho squared sine phi. That's your p function for all the spherical problems. We've got a few minutes. Was there anything else that you all wanted me to show, or anything that was sketchy when I wrote it down that you have clarifying questions about? For question 6, will it be relatively similar? Kind of. So this one's just tough because you have 2 surfaces to think about. So but luckily it tells you what's above and what's below. So it's saying above by z equals 2 and below by z equals x squared plus y squared. X squared plus y squared is like a forward thing. So this is going to be your lower z bound, and that's going to be your upper z bound. Like that, and you would just convert to the polar coordinates. It says see this figure in your textbook, but it's going to be about this. It's that shape. David, is that an answer to the question you were asking? And then Macy, I see your question. I'm going to do it next. Okay, great. And then Macy, having trouble thinking about the upper bound for rho on problem 3. Okay, so the upper bound for rho on problem 3 here looks tricky, except for it's actually the same as if you took this cylinder right here on problem 2. The part where we were thinking about rho going up to that flat part, it's actually the exact same on problem 3. We're only doing that flat part. So if you do the first half of the spherical coordinates for the cylinder on problem 2, that's exactly problem 3, basically. Like on problem 2, you're taking that, I don't know, flat cone thing, and you're adding this weird shape to it. Oh, sorry, the chat is blocking it. So problem 2 was taking this cone and adding the cylinder that it sits inside to it. Problem 3 is just doing the first half. And so to actually get that equation, ask yourself, like, how would I write a function for the top of this surface? That's where rho is going to. And then convert that to spherical coordinates. So for me, as ugly as it is, my cone has height 79. So if I wanted to write a function for this surface, it would be z is 79, because z is height to us. And then I would convert z to be something about rho, using z equals rho sine or cosine phi, and set that equal to 79 the same way we did here. Macy, is that answering the question you were asking? Okay, great. Thank you all for asking questions today. I'm gonna stop recording, stop screen sharing, and post this to YouTube. So if I went a little fast on anything, hopefully you can